The latest observation reports streaming into our facility are painting a chaotic picture. In just 1 week, 10 asteroids have been confirmed crossing the moon's orbital path. Then, a separate telescopic analysis confirmed an object grazed Antarctica at just 300 kilometers lower than most of our satellites. The alarming part, our early warning systems didn't detect it until it was already gone. We call this cosmic noise. It's a reminder that we're living in a galactic shooting gallery, but that noise, that's usually just the background. Currently, our full resources are focused on a single object, 2024 YR4. Our analysis classifies it as a city killer, large enough to obliterate a major metropolis on impact. For months, our orbital models here in the US all pointed to one alarming scenario. It was on a direct course for Earth. But then, in the last 72 hours, something strange happened. Its trajectory changed. Now, you might be thinking, great, that's good news. But with 30 years in this field, I can tell you, we don't believe in coincidences. A multi-million-ton space rock doesn't just change its plans. Gravity is a constant. That means something acted on it. A non-gravitational force. And here is the most baffling part of our latest update. 2024 YR4 is no longer heading for Earth. It is now on a direct vector for the moon. Why is this a cause for serious concern? Because last week, during a closed-door symposium on planetary defense, I spoke with an old colleague of mine, Professor Chen, from the Shanghai Astronomical Observatory. With their research stations and orbiters, the Chinese have more reason than anyone to be watching the moon. When I mentioned 2024 YR4, he didn't seem relieved. He seemed troubled. He told me their data suggested this new trajectory was too precise, almost unnatural. The question is no longer, is an asteroid going to hit us? Our question now is, why would a city killer perfectly alter its course to target the moon? And what does Professor Chen know about it that we don't? This is no longer routine astrophysics. We are entering the realm of the extraordinary. If you want to dive deep with me into the real mystery behind 2024 YR4 and explore the universe's most shocking secrets, hit that like button and subscribe right now. What we are about to find out might change how you look at the night sky forever. Still with me? Good. Because the latest observation report just got validated and it sheds light on exactly why Professor Chen was so worried. When my team first detected 2024 YR4 last December, it immediately hit our watch list. Why? Our initial calculations showed a 3.1% probability of an Earth impact in 2032. In my line of work, 3.1% is a sit-up and pay attention number. At an estimated 55 meters a city killer, it's large enough to release energy equivalent to several megatons. That is a history-altering event. Now, usually, as we get more observation data, these orbits get refined. And sure enough, by early 2025, our models confirmed Earth was in the clear. But this is where things get weird. Our latest analysis now shows 2024 YR4 has a 4% probability of impacting the moon in December 2032. 4%, to a layperson, that number sounds small, but to an orbital mechanic, that number is massive. It's almost a cosmic cold shot. For a random object, after being nudged by Earth's gravity, to settle into a trajectory so precise it has a 1 in 25 chance of striking the moon, that's what Professor Chen called unnatural. If it impacts, this won't just be a spectacular fireworks display. A strike from this 55-meter object would create a crater hundreds of meters wide. More importantly, it will hurl millions of tons of debris, lunar rock, and dust into space. And here's the problem. Much of that ejecta won't stay on the moon. It will be thrown back toward us. Our models predict a massive surge of fine particulates in low Earth orbit, LEO. Think about that. Thousands of satellites, our internet infrastructure, our GPS, and our top secret military assets would be flying straight through a cloud of cosmic shrapnel. This is no longer an astronomical problem, this is a global security problem. But even that threat isn't what's keeping me awake at night. It brings us back to the core question. What pushed 2024 YR4? A natural outgassing event from within? Possible, but the thrust would have to be incredibly precise. An impact from another unseen object? Highly improbable. Or was this a deliberate braking maneuver? What if the moon isn't the final target? What if someone or something needed this object to slow down and they're using the moon's gravity or even a grazing impact to do it? Professor Chen wasn't worried about his satellites. He was worried about why this rock is behaving like it's being steered. You see, if 2024 YR4 hits the moon, the problem isn't the moon. The problem is us. Our latest analysis shows an alarming scenario. If that impact occurs, the resulting plume of lunar ejecta could increase the particulate density in LEO by up to 1,000 times. This isn't just a risk. This is a Kessler syndrome scenario waiting to happen. It wouldn't threaten cities, but it could neutralize everything we depend on. Our communication grids, GPS, the International Space Station, and our defense assets. That's why planetary defense teams, both ours, and I'm certain China's are currently running mitigation models. We've tried this before. In 2022, NASA's DART mission was a success. We nudged the moonlet, Dimorphos. It was a huge win, right? Not exactly. The post-mission analysis revealed something we hadn't anticipated. The impact released an entire swarm of boulders from Dimorphos that no one saw coming. This proved an unsettling truth. We still don't fully understand how these rubble piles coasting through space are actually held together. And now, we are facing 2024 YR4. Our telescopic data has one massive gap. We do not know its precise mass. And that uncertainty makes any deflection plan incredibly risky. If we underestimate the mass, our nudge, like DART, will do almost nothing. If we overestimate the mass and push too hard, we could accidentally send it into a new resonant orbit, and the next target could be Earth itself. So, if a precise deflection is too risky, what's the next option? Destruction. One possibility is a high-velocity kinetic impact, basically, smashing it into smaller, harmless pieces. But there is another idea being discussed in back channels, a far more controversial one. A paper just published in September 2025, just last month, analyzed this exact scenario. It proposes using a 1 megaton nuclear device. Let me be clear. My colleagues in the United States are seriously running models on detonating a strategic nuclear weapon near the moon. Which brings me back to Professor Chen. He was worried because its trajectory was unnatural. And now, our response is to prepare an equally unnatural solution. What if 2024 YR4 isn't just a rock? What if it's something more complex? And what if smashing it, or worse, irradiating it with a nuclear blast, is the absolute worst thing we could do? We are flying blind, and we are bringing nuclear weapons. The internal analysis update I just saw confirms it. That September paper wasn't just theoretical. It details a height of burst detonation. Let me explain. You don't detonate the bomb on the surface, you detonate a 1 megaton device near it. The idea is that the intense wave of X-rays and radiation instantly vaporizes the surface layer, creating a massive asymmetrical rocket-like thrust to push it or shatter it, regardless of its precise mass. On paper, it's an elegant solution. I know that elegant solutions in space often have incredibly messy consequences. We've done this before. In 1962, the Starfish Prime experiment. We detonated a nuclear weapon in the upper atmosphere. The result? A disaster. It created new artificial radiation belts around the Earth. It fried satellites. That was in our own backyard. Now we're talking about doing it near the moon. And then there's the legal minefield. The Outer Space Treaty explicitly forbids placing nuclear weapons in orbit. Any mission like this would require an unprecedented level of international cooperation. Can you imagine Washington, Moscow, and crucially Beijing all agreeing to launch a nuclear warhead at an asteroid, especially one not directly threatening Earth? This brings me back to Professor Chen. The official line, the one you read in the press releases, is that this is all just a case study. They will tell you that statistically, there is still a 96% chance 2024 YR4 will miss the moon completely, sailing harmlessly into the void. And statistically, they are correct. But in science, you don't ignore the 4%, you investigate it. Especially when that 4%, as Chen put it, looks unnatural. Here is what Chen was trying to tell me. What if the 96% is the lie? Not an intentional lie, but a statistical one. What if the 96% represents the natural path, but the 4% represents the steered path? What if the reason planetary defense teams are calling this a case study is because they can't get the political approval to act on a 4% threat? This is where the real danger begins. Cosmic game theory. If the US is tied down by the Outer Space Treaty, waiting for consensus, but Professor Chen's data, the data he isn't publishing, suggests this threat is far more real. What will his government do? Are they modeling it as a case study, or are they quietly preparing a unilateral response? That 96% chance it'll miss, to me, that isn't reassuring. It's terrifying because it guarantees one thing: complacency. And in my field, complacency is what gets civilizations wiped out. And that is exactly my point. The 96% assumes we are dealing with a neat, predictable system. But the universe just gave us a massive lesson in that. The lesson of that, we thought we were performing a controlled nudge. Instead, we blasted a swarm of boulders into space that none of our models predicted. We keep making the mistake of imposing our order on cosmic chaos. Anyone who read Michael Crichton's original Jurassic Park novel remembers Dr. Ian Malcolm. He warned that nature rarely behaves in neat, predictable ways. This is the core concept my team is grappling with for 2024 YR4. Malcolm split the mathematical world into two categories. The first type, linear systems. Imagine you're driving on the freeway with cruise control. You tap the accelerator to go 10 kph faster, and the speedometer moves up exactly 10 kph. The input and the output match, like a straight line graph. That's linearity. It's predictable, reliable. This is how 96% of scientists are looking at 2024 YR4. As a simple rock, they think if we nudge it with a DART spacecraft or a nuclear device, it will respond linearly. But DART proved that even a simple rock isn't linear. And this is what has me and Professor Chen so concerned. The trajectory of 2024 YR4 is not behaving linearly. That sudden, unnatural orbital shift, it wasn't a 10 kph tap on the accelerator. It suggests we aren't dealing with a linear system at all. We are dealing with a second kind of math. And then there are nonlinear systems. Imagine a tinder-dry forest at the end of a long, hot summer. A single spark, one careless ember from a campfire, catches a patch of dry grass. The flame climbs a tree, jumps the canopy, and in minutes, the entire hillside roars like a blowtorch. The cause is tiny, the effect is massive, and unstoppable. Non-linear systems amplify. Tiny causes ignite massive effects. In 2022, we took a cosmic swing at a space rock. Not to blow it up, not to mine it, but simply to ask a question that sounds like it came straight from a late-night Reddit thread. If we punch an asteroid, does it move? That mission was DART, Double Asteroid Redirection Test, and that punch struck a small moonlet named Dimorphos, orbiting its parent asteroid Didymos, some 11 million kilometers from Earth. Our engineers started with perfectly linear textbook physics. The input and the output correspond perfectly, like a straight line graph. That's linear. And then there are nonlinear systems. Picture a tinder-dry forest at the end of a long, hot summer. A single spark, one careless ember from a campfire, catches a tuft of dry grass. The flame climbs a tree, leaps across the canopy, and in mere minutes, the entire hillside is roaring like a welding torch. The cause is tiny. The consequence is vast and unstoppable. Nonlinear systems amplify. Tiny causes ignite massive effects. Keep that idea in mind. Momentum is defined as mass times velocity. If you know the mass of the spacecraft, DART, and its impact speed, you can calculate exactly how much push it's going to deliver. It's a neat linear equation. We expected a neat response. We were anticipating a 10 kilometers per hour nudge on the highway. But the universe, as a certain Dr. Malcolm warned, is rarely neat. Apply that nudge to Dimorphos, and you can predict precisely how much faster that little moonlet will complete one orbit around its parent, Didymos. Based on our linear calculations, scientists predicted the impact would shorten the asteroid's orbital period by about 73 seconds. A clean push. But what actually happened was this. When DART slammed into Dimorphos, it shortened its orbit by 33 minutes. 33 minutes. That is over 25 times more than the baseline prediction. Now, you might be thinking, that's not bad, that's better, a bigger push. The test is still a win for planetary defense, right? The universe rarely hands out clean victories. 2 years later, as astronomers dug into the aftermath data, they discovered the orbital shift was just the opening act. That impact was a small spark. The reaction was nonlinear. Something else happened that day. We didn't just move an asteroid, we unleashed a boulder swarm, the unexpected swarm. Our latest telescopic analysis comes from images by Lysia Cube, a suitcase-sized probe that trailed DART. And now, a new study, just published by astronomers from the University of Maryland, has revealed the truth, where there should have been a conical cloud of fine dust. There was instead a jagged halo of more than 100 large boulders. Some were no bigger than a loaf of bread. Others were as large as compact cars. And here is the most alarming part of the Maryland report. They were not drifting passively. That's right, sprinting is the word the latest Maryland analysis used. Many of the boulders were moving at speeds over 50 meters per second. This wasn't a nudge, it was a detonation. When researchers reconstructed their motion, they discovered something astonishing. That ejecta carried 3 times the momentum of the DART spacecraft that spawned it. Let me stress that. The recoil was more powerful than the bullet. This changes everything. Our entire concept of a kinetic impactor was linear. You use the spacecraft's P equals mv to move the asteroid, but those boulders change the equation. The debris blasting off the surface added an extra push, a kick, almost as powerful as the initial impact itself. The true DART impact wasn't an event. It was a 2-stage event, the initial collision, followed by a chaotic high-velocity explosion of rock fragments. That is why the 73-second linear prediction became the 33-minute nonlinear reality. And if that wasn't enough to worry us, the Maryland report pointed out something even stranger. The boulders weren't scattered randomly. Instead, they were clustered into two distinct groups, with a void of material elsewhere. Again, this isn't natural. It implies something unidentified is at play here. Now, what's the official stance? Researchers are digging deeper into impact physics, so future planetary defense planners have solid data when choosing a kinetic impactor. This means we have absolutely no idea what we're doing. We punched an asteroid, and it reacted in a way nobody could have predicted. And this is what brings us back to Professor Chen and 2024 YR4. Chen saw this chaos. He knew that when you hit a rubble pile, it reacts non-linearly and chaotically. So why is he worried about 2024 YR4? Because 2024 YR4 is doing the opposite. Its trajectory is changing precisely, cleanly, and predictably to target the moon. It is not behaving like Dimorphos. It is not behaving like a chaotic rubble pile. And if we, with our nuclear plan or our DART-2 scheme, approach 2024 YR4 thinking it's a rock, when it is something else entirely, that something unidentified was at play during the DART impact. And I have a feeling that something unidentified is also at play right now on 2024 YR4. This isn't news to my team. These latest analytical reports from this past April and August just confirm what we already feared. We didn't just push an asteroid, we turned it into a cosmic shotgun. Think about that. The April 2024 report noted we may have accidentally hurled massive boulders at Mars, potentially endangering colonies for the next 6,000 years. The August report showed smaller fragments are heading earthward due in 30 years. We created our own mess. We proved that when equations leave the whiteboard and meet reality, reality wins. Chaos wins. The anomaly wins. The unexpected wins. Space rocks don't come with smooth surfaces or easy predictions. They come with chaos. This is the DART lesson. And this is precisely why the ESA, European Space Agency mission, HERA, is so critical. HERA is our crime scene investigator. It is currently en route to the Didymos-Dimorphos system and is set to arrive in late 2026. It will survey the mess DART created and tell us exactly what happened. It will measure the mass, inspect the crater, map the boulder swarm. It will provide the solid data we are missing. But here is the fatal problem. HERA arrives in late 2026. The trajectory of 2024 YR4 is being decided right now. We are being forced to make plans at DART-2, a nuclear option, for an object that is behaving bizarrely, while we still don't understand the results of the only test we've ever run. And this brings me back to Professor Chen and his terrifying silence. Chen knows all of this. He's seen the chaotic DART data. He knows HERA is 2 years away, and he also has the telescopic data on 2024 YR4. The reason he's worried isn't just that we might blow up the moon. He's worried because his data must be showing the same thing mine is. 2024 YR4's orbit changed cleanly. No chaos. No surprise boulder swarm. No 25x nonlinear reaction. How does a city killer execute an orbital burn more precisely than NASA's multi-million-dollar DART mission? Chen isn't afraid that 2024 YR4 is a rock. He's afraid that it is not. That's right. HERA is our ground truth. Unlike DART, which was the hit and run, HERA will stay. It will map the crater in high definition. It will measure the mass. It will study the boulder swarm. And most importantly, it will tell us if the chaotic, nonlinear behavior we witnessed continued for days, months, or even years. This data is vital because DART was one experiment. We can't use it to know how to handle every asteroid. Some will be dusty, some will be icy. Others, like Dimorphos, are boulder-filled rubble piles. Each one is a totally new challenge. And this is the brutal truth, folks. This is what keeps me and my colleagues up at night. We do not have that data right now. Hera gets there in late 2026. 2024, YR4 is here now. Our planetary defense teams are flying completely blind. We are being forced to make plans a nuclear option, a DART-2 for an object targeting the moon, while we don't even understand the results of the only experiment we have ever run. We learned from DART that when you punch a rock, it reacts with chaos. And this brings me back to Professor Chen, and the real reason I'm making this video series. Here in the States, we are debating is 2024 YR4 dust or rock. We are trying to apply the chaotic DART lesson to it. But I can't shake Chen's words. Not natural. What if the reason 2024 YR4 isn't behaving chaotically is because it's not a geological challenge? We're gearing up for a fight against a rock. We're worried about dust and ice. What if Professor Chen is silent, not because he's afraid we'll blow up the moon, but because his data, the data he refuses to share, shows that 2024 YR4 isn't an it? What if it's a day? What if 2024 YR4 isn't a rock, but a vehicle performing an intentional braking burn using the moon? And while we are arguing about using a nuke, they are preparing for arrival. The universe isn't just a shooting gallery. It's a place full of surprises. And I'm afraid we just found the biggest one yet.